Okay, welcome to part 2 of Leaving My Career in Tatters. Nathaniel asked me to present this on his behalf. Unfortunately, he was not able to make it. He's understandably attending the Aura workshop that's happening this week. So is this going to work? Yes, great. I'm sure we're all fairly familiar now with the role of the UTLS in the Earth system and poor representation of key processes in the upper troposphere and lower stratosphere in models being a significant barrier to meeting the improved understanding on the sort of minute to week and seasonal to decadal timescales that measurements are required over. In the UTLS, where the impacts of water vapor and ozone are greatest, this area is really characterized by strong gradients and large spatial and temporal variability, as well as long chemical lifetimes of different species and the long-range transport of certain pollutants. The idea is that there's poorly understood variability in the stratospheric water vapor that significantly affects things like surface temperatures and the ozone layer. So the Aura MLS, the picture over on the right there with a man for scale, I guess. It's kind of a big beast of an instrument. Aura had a total of 4 instruments on it when it was launched in 2004. And MLS measures 16 trace gas species along with temperature, geopotential height, and cloud properties. I guess this is a bit of a boast. There's lots of papers on Aura MLS observations over the years, and there have been several reviews to keep running the instrument. It's been very fruitful and is really a high priority mission for NASA. So there's various different channels over which the instrument has measured these number of things, and there's a sort of representative orbit pattern. I'm sure you're all far more familiar with this than I am. The reason, I guess, why Nathaniel isn't here is that Aura's status is being considered this week. And so... maybe I don't need to talk through like every single point in here, and we can get on to actually talking about continuity. But essentially, the panel that's happening this week is going to review all of the white papers or RFIs that were submitted. And Nathaniel wanted me to say thank you to those in the room that put together some of these papers, arguing for MLS's continuation. I think he was really impressed with the community support for Aura MLS. Hopefully, if Aura does get extended, then it can continue operating into mid-2025, possibly early 2026 if they're lucky. And then at that point, there'll be insufficient power, and I think the solar arrays are degrading over time and it's running out of fuel. So, yes, a great shame. So, Aura versus continuity MLS. So, the proposed plan was to reduce the size, weight, and power, as well as the sensitivity, as well as increase the sensitivity of the instrument. And so, due to profound innovations in recent years, driven by the comms industry, they've been able to really reduce the potential mass, power, and volume for a future MLS mission by down. I thought there was a factor on the scale, but I guess not. But so the only thing that really is limiting the size of the instrument now is the antenna, which still needs to remain large so that you can fully image the limb. So Continuity MLS, the ESTO IAP project started this year, and they will. The overall goal of that is to develop an Earth Venture commission instrument. And so what they're trying to show with this is the reduction here in size and power from 500 kilogram, 500 watt instrument down to 70 kilos and 90 watts itself. So they are crossing off a few of the target molecules that AuroMLS was able to measure, but they are planning on adding on others, including formaldehyde. The scope of the instrument in terms of the different channels is going to change slightly, so it's mainly going to focus on 340 and 640 gigahertz with a sideband separated 340 gigahertz channel and a folded sideband 640, which is more like the AuroMLS. So yeah, here's the sort of general overview. So up on the left-hand side, this is the current CAD model for continuity CMLS. And so, yeah, some of the major innovations have been the shrinking of some of the spectrometers and the IF processors. So that I'm going to show some of the pictures of the IF processor later, but you can see an example of the 40 centimeter long 25 channel spectrometer on the far right, and then in the middle the new 4000 channel digital spectrometer that's on a 5mm by 5mm chip, which is quite amazing. And yeah, this is kind of similar to my talk, I guess. There's the kind of high-level block diagram here for the instrument, which shows the beam coming in through the antenna, switching her again with various calibration targets, and then they have this really cool beam splitter that allows them to separate the 640 and the 340 gigahertz. And then that's passed through the back end to through IF processing and spectrometers to CNDH. So yes, I think so. Yeah, here's kind of like a representation of the folded sideband way that AuroMLS used to operate. So essentially taking the lower and upper sidebands and combining them on top of each other. And so this is kind of problematic in a couple of ways, but essentially you're sort of doubling your noise. Some of the noise mixes in with the signal that you're interested in. So in this particular case on the far right, you can see this red spectral signal is quite small in comparison to the wings of the water continuum here. So one of the ways of reducing that uncertainty from the folded sideband technique is to do sideband separating. And so that's what they're working on right now. So one of the ways of doing that sideband separation is to just simply have a beam splitter in the path, but obviously this can be quite lossy. So they've come up with this design for a sideband separator that's based on this sort of microchannel waveguide technology that's pretty cool. So if you see on the right here, there's the beam splitter in action, and actually I've just remembered this was supposed to be an animation and it kind of oscillated and showed the waves passing through. But yeah, essentially based on the geometry of those channels, they're able to separate the 340 and 640 gigahertz right here with like minimal losses. And yeah, you can see down the bottom here on the left how good the rejection is down to 30 dB or something like that. Yes. So then here is some of that technology in action. So this is like on a test setup in the lab. And so there's a tone generator that they're using to test out the beam splitter technology. So they generate an 85 gigahertz tone, and it goes through a series of amplifiers and doublers to get up to the 340 gigahertz that they need. And then, yeah, they've been testing various parts of the technology using this setup. And here's one of the other innovations is the new micro IF frequency subsystems. So much like the spectrometer technology, this has shrunk amazingly. The one that we have on ASMLS is, sort of 30 centimeters by 30 centimeters with a load of little modular components all plumbed together. And, you can see from these pictures, these are SMA connectors on here. So these things are really, really tiny. So this has really been part of the technology development was to get this really nailed down. And so they're testing this technology right now. So yeah, in summary, there's hopefully going to be a continuation of the Aura mission beyond 2023, but it's not assured yet. Despite that, Aura would be expected to cease operations sometime in 2025, maybe early 2026. CMLS is currently underway. You saw some of the technology being developed. They've made, like I said, some of these key components, and they're just getting into some of the testing right now, and hopefully this will turn into an instrument that lends itself really to some future NASA programs, including Earth System Explorer and Earth Venture Continuity. And once again, Nathaniel was really apologetic that he couldn't make it, and he thanks you all for his support of Aura MLS, certainly in the last few years. So thank you very much.